In the last video, we talked about the introduction to the numerical methods. Okay, when do we use numerical methods? Is if it is complicated problem to find out the exact solution, or if the exact solution does not exist, then usually we use the numerical methods. Okay, but the numerical method we talked last time is a very basic, very primitive, and very easy to calculate, but it is not a perfect method, meaning that it has some error. Okay, because you see that when we did that method and then when we plot the graph of the exact solution and the graph of the approximate solution were different, right? Meaning that when the value of the h, the step size, was decreased, then the graph of the approximate solution was close to the graph of the exact solution, but not the exactly same. Okay, so the difference at any time t, the difference between the exact value and the approximate value is called the error, right? You see that this was the Euler's method, right? So yn plus 1 equals to y sub n plus h times f of t and yn, and y of t at t0 is y0. This was the initial value problem where t sub n is t0 plus n times h, and you plug in that t0 and y0 to find out y1, and then t1 and y1 to find out y2, and so on, and you plot the tn, yn, the order pair, the pair of the points, right? And then you get the approximate solution. Now, how do you find out the error? Error is the exact minus the approximate. Okay, so for example, if you are to solve dy over dt equals to 1 minus t plus 4y, and then y0 equals to 1, if this is the initial value problem, this is the initial value problem, okay, and then these are the values. If you take h equals to 0.05, you find out t0 y0, t1 y1, t2 y2, t3 y3, and so on, and then you plot the values. Okay, and then whenever t equals to these values, if you are finding the value of y's, value of the solution of this at different time points, look at this, at h equals to 0.05, when h is 0.05, when the step size is 0.05, these are the values you get. When the step size is 0.025, these are the values, 0.01, 0.001, and the exact, meaning you solve this and you find out the exact solution of the equation, and then you plot the values of t equals to 0, 0.1, 0.2, and so on. These are the exact solution value. Okay, let us pick some point there. Let us pick t equals to 0.05. When h is 0.01, what do you get? Yn is, or you can say y at 0.05. The approximate value of y at 0.05 is 8.3767 when you round up, right? Similarly, at h equals to 0.001, the value is 8.6771. You see that? And these are the exact values. Okay, what we did here, we decreased the value of h, or the step size, by 10, by a factor 10, right? Because 0.01 divided by 10 is 0.001, right? When we decrease the step size by a factor 10, so by what factor the error decrease? Let us find out the error first. What is the error when h is 0.01 and at t equals to 0.5? The error is basically the exact value minus the approximate value. This is what you will get. Error is 0.3353, because what I did is I did this minus that value. And when I decrease the step size from 0.01 to 0.001, the error is this exact value minus the approximate value. You will get 0.0349. You see that we decrease the step size by a factor 10, and you see the error is decreased by a factor 10 almost, right? Almost. So here, by whatever factor you decrease the step size, the error is decreased by the similar factor. Okay, or we can say that the error is almost proportional to the step size. The error is proportional to the step size at any time t. That's what this method follow. Okay, that is, the error is less or equals to a constant times the step size. Okay, so this has the exponent 1. You see that? So k times h to the 1. So we say that this Euler method is of order 1 method. Okay, so the Euler's method is order 1 method. So that is, there is h to the 1 order 1 method. So if sometimes in some other method, we will see that later, whenever you decrease the step size by 10 factor 10, the error will decrease by factor 100 or 1000, like that. So we want that type of method, right? Because that will basically approximate the solution better and faster, right? So the next thing we will do is we will try to see some other method that has a better approximation, meaning that the error is smaller. Okay, so the next method is on 8.3. We talk the improved Euler method. This is the formula for the improved Euler method, similar to this one. The formula for the improved Euler method, by the way, so y at t0 is y0, right? This is the initial value problem. So suppose you have a differential equation dy over dt equals to f of ty. So this is the differential equation with the initial value like this, right? If you want to solve this initial value problem, then the method is, the improved Euler method is similar to the Euler method, but it has the order of the approximation or order of the convergence, you say, the order is better. It will be order 2, meaning that we will write that the error is proportional to the h square. Error with step size h is proportional to the h square, which means error of the approximation is less or equals to k times the h square. Okay, so the error will be less or equals to a constant times the h square on the improved Euler method. Okay, so how does this method work? The formula is y sub t n plus 1 equals to y sub n plus h times, this is the average of f of tn yn plus f of tn plus h, yn plus h times f of tn yn. Okay, and then y sub t0 is y0. So this is the initial value. So this is the formula for the improved Euler method, and this method is of order h square. Okay, so let us see this exactly same example. I will do couple steps by hand, and then I will show you a full table what you get for different step size. Okay, so I want to solve this by hand. Okay, so let us solve this example, exactly the same example. So what you want to do is you want to solve by solve the equation dy over dt equals to 1 minus t plus 4y, and then y of 0 equals to 1 by using the improved Euler method. Okay, so here what is f of ty? That is 1 minus t plus 4y, right? What is f of tn yn? That will be 1 minus tn plus 4yn, right? I just replace a t by tn and y by yn. Okay, so so what we have to do there is we will have the column for t, okay, and then column for yn, and then the tn yn, right? So but what values of h do you take? Let h equals to 0.025. I have to take h equals 0.025. What else is given? T0 is given as 0, right? And then y sub 0 is given as 1. So T0 and y0 are given, and then we will plug in here, right here, to find out yn plus 1, right? So with this value, what will be our f of tn yn? So f of t and f of t and yn, let's find out f of t0 y0, because I will need that here, right? F of t0 y. If you want to find out y1, you will take n equals to 0, it will give you y0 plus h times h is 0.025, right? And then f of t0 y0. Let's find out f of t0 y0. 1 minus t0 plus 4y0, right? What do you get? If you plug in those values, what do you get is 5, because it is 1 minus t0 is how much? 0 plus 4 times y0 is 1, that is 5, right? Also, what do I need for if you want to find out y1, you will need this value, right? So what is that? F of t0 plus h comma y sub n plus h times f of t0 y0. This is also we will need to find out y1, right? So what do you get here? You will get, so 1 minus, so let me plug in that, because what is f of t and yn is that, right? So f of t0 plus h minus that thing will be 1 minus, it will be, when there is tn, it will be minus tn, right? So it will be t0 plus h. That's what you will get, right? And then plus 4 times the second component, right? So y of 0 plus h times f of t0 y0 is how much? 5. That's what I will plug in there. Okay, now let us see that 1 minus t0 is, what is t0? T0 is 0 plus h is 0.0, so 1 minus 0.025 plus 4 y0 is how much? Y0 is 1 plus h is 0.025 times 5. Let me write that times there. If you simplify that, you will get 5.475. So from this you can find out y1, right? From this one we will get, hence, so y1 is equals to, you just use that formula. What will be y1? You take n equals to 0 in the formula, right? So you will get y0 plus h is 0.025 bracket. What is f of t0 y0? You got 5. You see that? And then plus, what is that value? F of t0 plus h, right? What is h? H is 0.025, right? You plug in that, you will get 5.475. 5.475, right? And then divided by 2. You see that? This is what you get. So if you simplify that, you will get 1.1309. 1.1309. This is what you will get. Now you continue that process, right? So what you do next is you will find out next. What you do is you will find out f of t1 y1, right? You just continue from here, right? F of t1 y1 will be 1 minus t1 minus 4 of y1. You see that? What is t1? T1 is n equals to 0, right? So it will be basically t0 plus, yes, so tn is t0 plus n times h. Okay, so this will be, so let us write down that. What do I write there is t sub n equals to t0 plus n times h. Okay, so t0 plus n times h. So if you do that, what will be t1? T1 will be t0 plus 1 times h. That is 0 plus 0.025, right? So 1 minus, let me use this. So it is 1 minus 0.025, right? Plus 4 times that value, right? So 1.1309. It is better if you consider more decimal places, right? This will give you 49875. This is what you will get for f of t1 y1. Okay, so similarly you need to find out that, okay, f of that, and then you find out the y2 value. So continue that, you will find out f of t1 plus h comma y1 plus, by the way, this would be y0, okay, plus h times f of t1 y1. This is what you will find out. Okay, so what do you get? You will get this value will be 6.023625. 6.023625, and then finally you plug in that formula. So y2 will be, you just plug in that 1 minus t1. T1 is, oh, by the way, so y2 is y1, right? Yn plus, right? So it will be y1 plus. So what is y1? So y1 is 1.1309, 1.1309, okay? And then plus 1/2, and then you plug in those values, you will get 5.49875 plus 6.023625, and then times, what is our h? Oh, by the way, I forgot to, this is divide by 2, right? And then you write h here. H is 0.025, okay? So h is 0.025. If you do that, you will basically get 1.274967, and continue that way. Okay, if you continue that way, you will get the values of like t, right? And then h equals to 0.025, and then so you can say tn, right? And then yn, and then if you plug in those tn and yn values, then you will get the solution curve. Now I will show you how does that look like, and then I will show you how does the error changes. Okay, how does the error change when you plug in, when you take h equals to 0.025 and h equals to 0.01, and I will show you how the error changes on this method. Okay, in the table that I'm going to present, you will see a column of t, that is the first column. Okay, I am recording only the values of t equals to 0, 0.1, 0.2, 0.3, 0.4, 0.5, 1, 1.5, and 2. But when you calculate this, what is this f of t0, y0 means? This is basically y sub 0, t sub 0, right? T sub 0 at y sub 0. This is 1 point, right? T sub 0, y sub 0 is 1 point. What is that point? This is basically 0, 1. 0, 1, right? What will be t1? Because your h is 0.025, right? So another one will be 0.025, and then what is the value of y1? 1.1309. 1.1309. This is basically the second point. And then similarly you find out the third point, 0.05 comma, and then 1.2709, because this is the point when t is one step further away from that, right? This is because h is 0.025, that's why this is 0, this is h, this is t0, t0 plus h, t0 plus 2h, t0 plus 3h, and so on, right? So I am not recording all those values. I am recording only for 0, 0.1. 0.1 will be 2 step after this, right? Because the next one will be 0.075, and then you will be 0.1 after that. You will get those. So I am recording only that value on the table. Okay, not all these values. I am skipping those values and recording just that on the table. Okay, let me show you that table. Look at this one. When h is 0.025, this is for t0. Okay, this is for t0. This is for t1. This is for when t equals to 0. This is when t equals to 0. When this is when t equals to 0.1, t equals 0.2, t equals 0.3, 0.4, 0.5, 1, and then 1.5, 2, and so on. Okay. Now, what I'm going to show you here is, look at the step size h is 0.025. Here the step size h is 0.01, which is smaller than, right? So it is smaller by factor 2.5. Okay, because that divided by 2.5. Okay, this one divided by 2.5 will give you 0.01. Okay, let us see how the error is changing whenever these are the y values, right? When you have, these are the approximated y values. Let us see how the error is changing. Okay, let us say, for example, This is t equals 0, 0.1, 0.2, 0.3, 0.4, 0.5. Let us see for these values. Okay, for these values, look at these two values. When t equals to 0.05, this is the approximate value of y under h equals to approximate value of the solution y, right? Under h equals 0.025, and this one is under h equals to 0.01. You see that? This is under h equals to 0.01. Now what do you see there is, what is the exact value? Exact value is 8.7120041. Okay, so now let us see the error. So when h is 0.025, the error is this minus that. What do you get? So at 0.035, what you get is the value of y sub n, or the value of the solution at t 8.684904, right? And then for h equals to 0.01, you will get 8.7074637. And what is the exact value? Exact value is, you will get 8.71200041. Okay, so this is the exact value. Now what do you see? What is the error? So error on this will be 0.0271, and error on this is 0.000044. You see that? So what? How did you? By what factor did you decrease the value of h? Is by 2.5, right? But here the error is decreased by even more than that, right? Because it is not decreased by the same ratio. You see that? It is decreased by, the error is decreased by. So basically what we did is we decreased h by 2.5 factor, right? And then error decreased by 6.16. It is almost the square of that, right? Square of that. So 2.5 square is 6.25, almost that. So that's why what I wanted to say here is, the improved Euler method is of error h squared, meaning if you decreased the step size by h, then you will see the error will decrease by h square. Okay, so error will be decreased by almost h square, meaning that it will be smaller than k times the h square. That's why we call this method is of order 2 method. Okay, so order 2 method. So basically this will give you better approximation than the Euler's method, and I'm going to give you one more method that is called Runge-Kutta method. Okay, so that method is of order 4, meaning that if you decrease the step size by h, then the error will be decreased almost by h to the 4. So order 4 method. So I will give you the formula for that, and hopefully I will be able to present one example for that too. Okay. The third and the most powerful method that we are going to discuss on this section is the Runge-Kutta method. Okay, we also denote by RK4. The reason is this method is fourth order method. What that means is the error is proportional to the fourth power of the step size. Okay, that means this should be error. The error must be is less than or equals to a constant times the fourth power of the step size. So this is the formula. Okay, so basically we are talking about the different numerical method to solve this initial value problem. Dy over dt equals to t function of t and y on the right side, and then the initial condition is y t0 is equals to y0. The formula, the RK4 formula, the Runge-Kutta method formula is y sub n plus 1 equals to y sub n plus 1 over 6 times h times kn1 plus kn2, 2 times k12 plus 2 times kn3 plus kn4. This is the formula. What are the values of kn1, kn2? These are the values of kn1, kn2, kn3, kn4. Okay, so kn1 is whatever you got in the right hand side. Kn2 is tn is updated by tn plus h over 2, and then yn is updated by yn plus h over 2 times kn1. That kn1, you see that kn1 is here. Similarly, others kn3, kn4 are similar, but what you do, the first component is same on kn2 and kn3. The second component here, you use kn2, that value, you use that value, okay? And for kn4, you don't have h over 2, just h plus y sub n plus h times k. Oh, by the way, this is n2, okay? This is n2. So kn2, n2, not k to n, okay? So kn2, this is kn3. So this is kn3. Okay? So this is the formula for the Runge-Kutta method. So let us do one example. The exactly same example we did before. So dy over dt equals to 1 minus t minus 4y. y0 is 1. So what you do? Let us pick a step size h equals to 0.2. Then you find out k01. What is k01? K01 is whenever n is replaced by 0, then it should be t0 y0, right? t0 y0. So how do I find out t0 y0? This is f. You see that? This is the f of tn yn is 1 minus tn minus 4yn, right? Yn. So you replace n by 0 and 0. You will get 1 minus t0 minus 4y0, which is 5. What do you do? Because the value of t0 is how much? The value of t0 is 0, right? And then what is the value of y0 is 1. So sorry, this is plus. This is plus. Okay, this is what you get, 5. Similarly, oh, this one is also plus. Similarly, k02 is t0 plus h over 2, because we are replacing n by 0. So you need, for n equals to 0, you need to find out all those 4. And then after you find out these values, you update the y0 will become y1, and then y1 will be y0 plus h over 6. That formula you plug in that. And then next you pick n equals to, so n equals to 1, n equals to 2. You will get, when you take n equals to 1 and plug in here, you will get y2. And take n equals 2 and plug in here, you will get y3, and so on. So you continue that way, okay? So you find out k02, k03, k04, just plugging into that formula, you will get those values. And then to find out y1, just use that formula, replace n by 0, right? So you plug in that, and then just plug in those values, k01, k02, k03, and k04, plug in from here. You see that? k02, k03, k04. And then your y1 is that. To find out y2, just take n equals to 1. k11 will be t1, f of t1 plus y1. What is f of t1 plus 1 minus t1 plus 4y1? So what will be t1? T1 will be, so because tn is t0 plus n times h, right? That's what you do. So t0 is 0, n times h is n is, when when n is 1, you'll get t1 is 1 times h. H is 0.2, so 0.2. So t1 is 0.2. Okay, and then what will be y1? So because when you plug in here, you will get f of t1 y1. Y1 will be that value. You see that? Similarly, t1 plus h over 2. So t1 is, what is t1? T1 will be 0.2 plus 0.2 over 2 will be 0.1. So 0.3. This will become 0.3. Similarly, you just plug in that values and get those. So and then you find out y1, y2, y3. So I will show you the table, okay, for all those values of y1, y2, y3 for different values of k. K equals to 0.2, k equals to 0.1, k equals 0.5. I will show you all those values in the table. Now let us see this node. What does it say is whenever k equals 0.2, t0 will be 0, right? T1 will be t0 plus h. That will be 0.2 because this is 0, right? 0 plus 0.2 will be 0.2. This will be 0 plus 2 times 0.2 will be 0.4, and t3 will be 0.6, and so on. But when t equals to 0.1, then t0 is 0, t1 is 0.1, t2 is 0.2, t3 is 0.3, and so on. You will see in the table that when k is this is h, okay? When h is 0.2, when h is 0.2, this is also h. I'm sorry about that. So this is when h is 0.2, that's what you get. When h is 0.1, this is what you will get. So in the table you will see that when h is 0.2, you will see that the values of y will be when t equals to 0.2, 0.4, and 1 and 1.5 for whatever value, and 2 like that, right? But when h is 0.1, you will see in the table for t equals 0.1, you will see a value 0.2, 0.3, 0.4, 0.5, and 1. So you will see all those values in the table, okay? So, but when h equals to 0.2, you will be missing 0.3, 0.5 like that. The reason is because we will not be able to find out the value of y for t equals to 0.3, 0.5 like that, okay? All right. So let me show you the table next. So here I am presenting all the values, the table values by 3 different methods that we learned. Okay, on the very left, this is the Euler's method. The example is same example that I just took, 1 minus t plus 4y, y0 equals to 1, right? Look at this one. When t equals to when h equals to 0.05, 0.025, and then h equals to 0.01, h equals 0.001, and these are the exact values. This is by Euler's method, okay, and this one is by improved Euler method, and this is for by Runge-Kutta method, okay. So we will see which one is doing better job to approximate the exact values, right? So let us look at time t equals to 2. So when h equals to 0.05, the value of the y, the approximated value of the solution at t equals to 2 is 1745, okay, while the exact value is 3540. It is just half, okay, it is very far away. You see that? With the Euler's method, the approximated value at t equals to 2 and the exact value at t equals to are very, very different when h equals to 0.05. Even when h equals to 0.001, very small step size, you see that the exact value is far away from the approximated value. It is not as far when h equals 0.05. When you decrease the step size, the error is decreased, error is lower, but the value is not very close, right? Because there is 16 plus 40, almost 56 units away. You see that? But when you go to the improved Euler method, you see that. So when you have the h equals to 0.025, it is 3496. When h equals 0.025 here in the Euler's method is 2432 versus 3540 for 0.025. You see that? So which is a lot farther away, right? And when h equals 0.01, it is 3029. For h equals to 0.01, it is 3532. So it is closer to the exact value, but this one is not close to the exact value. But this one is better, right? Because you see 3540 versus 3532. So 8 units away for h equals 0.01. What we can see is for both methods, you see that when you decrease the step size, you will decrease the error. Okay, so this method is order 2 method. The improved Euler method is order 2 method. Euler's method is just order 1 method, meaning if you decrease the step size by some order, okay, then the error will be decreased by the same order. You see that? And but in the improved Euler method, the error will be decreased by the square of the order, meaning that if you decrease by factor 5, then the error will be decreased by factor 25 and so on. Almost, right? Because it is the proportional thing. And when the Runge-Kutta method, it is order 4 method, meaning that if you decrease the step size by some order, okay, some number, then the error will be decreased by 4th power, the factor of 4th power of that size. Okay, so you see that for h equals to 0.2, which is a lot bigger, you see h equals to 0.05 is here. For h equals to 0.05, look at the value. At t equals to 2, the value is 3539, almost 3540. You see that? It is very, very close. Even for the biggest step size. Here, we took the biggest step size here. Among all these step size, this is the biggest step size, right? In this case, when t equals to 0, the y value, the approximate value is 1745 versus the exact is 3540. Here, for h equals to 0.05, same h value. For t equals to 2, you see the 3539.88, which is almost 3540, right? You see the exactly very small errors, almost equal to the exact value. So that's why we say the Runge-Kutta method is the best among all these 3 methods. Okay, So alright, so next thing we will do is I will show you all these things. I will compare the Runge-Kutta and then the Euler's method in the MATLAB. Okay. Alright, let us see the examples we just did by different methods using MATLAB. Okay, first of all, I will show you the Euler's method. There are so many ways you can write a code. For the Euler's method, it is the simplest type of method. Okay, so yesterday in the last video I was showing it slightly differently, but in this video I'm doing the same thing but slightly differently. So what I did here is I defined the function 1. I named the function 1 at t1 y1. So what was the function we took in the video was 1 minus t1 1 minus t plus 4y. So dy over dx dt equals to 1 minus t plus 4y, right? So what I did here is I named it f1. Why did I do f1? Because I will give a name f for when I use the different method. Okay, so this is the Euler's method I'm using. So f1 is t1 y1, 1 minus t1 plus 4y1. It is 1 minus t plus 4y. Actually, since I gave t1 y1, so I replaced t by t1, y by y1. Okay, so h is the step size. I gave 0.5. So t1 final, how big x-axis do I want to see? From 0 to 2.5. That's what t1 is. 0 to with h is the step size, and then go up through t1 final. Okay, so what is the exact solution? Exact solution is solved by hand, and this is the exact solution we found. So actually I did not derive this exact solution, but this is given in the book, so I just wanted to compare the exact solution with the numerical solution. Okay, so these are pretty standard. y1 is zeros from 1 through the length of the t1, and then y1, this is the initial condition. Okay, so this is the initial condition. Okay, so when you give the percent sign, that will comment, and that the code will not, or the MATLAB will not execute after the percent sign. This is the commenting. Okay, just to clarify yourself. Now what I do is for n equals 2 to the length of t1, y1 n is y1 n minus 1 plus h times f1 t1 n minus 1. So this is the formula, right? So what is the formula for the Euler's method? It was y sub n equals to y sub n plus 1 equals to y sub n plus h times f of tn yn, right? So basically when you write, this is the Euler's formula, but if you write in the MATLAB, how do you write? Y of n plus 1 equals to y of n plus h times f of tn, and then comma yn, right? This is what you do. So but if you replace n by n minus 1, what do you get? You will get yn equals to y n minus 1 plus h times f of tn minus 1, right, comma, and then yn minus 1. So this method is, this code is easier because you don't have to find out what is f, because since you already defined f, okay, since you already defined f in line 3, so you don't have to type that function here. So you just type f1 and then tn minus 1, t1 n minus 1, and y1 n minus 1. That's what you do, and then you display t1 and y1 here. So now what I do next is I plot t1 versus exact solution, and then that will be colored red, and t1 y1, that is the approximate solution, with that will be dotted with color green. Okay, the line width is 3. Let me run that file. This is what you will see. Okay, so the red one is basically what is the red one? Red one is the approximate, red one is the exact solution. But you see, the Euler's method does a very poor job for this problem. You see that the error is very big. The green line is the approximate solution and the red line is the real solution. Okay, so you see that the Euler's method doesn't do good at all. So one of the reason maybe the function itself or the solution itself is like that. The other reason maybe because our h is big enough, right? Because h is 0.5. So if you do h equals to 0.05, if you decrease the step size, this is what it looks like. You see that? H equals to 0.5 give you a little better approximation. If you do one more 0, h equals to 0.005, it gives you almost the almost the same solution as the exact solution. But what is the problem? Why don't I take h equals to 0.005? The reason is because when you do h equals to very small value, then this code will run many times. Why is that? Because you see that when h equals to 0.5, the t1 will be 0 and then 0.5 and then 1, 1.5, 2, 2.5. That's it, right? So only 5 steps will be there. But if you do h equals to 0.05, in that case it will be 0 and then 0.05 and then 0.01, 0.015. There will be so many such steps, and then the computer will have to calculate that many steps. So in other words, it is more expensive, it is more time consuming. So you want to use the method that gives you a lower error with the higher step size. Actually, I am doing exactly the same thing, except what I am doing is I am copying the RK4, the Runge-Kutta formula here, okay, and I am displaying the Ti and Yi, and I am plotting that T and Y. Let me run that code. You see what you see here is even the step size. What is the step size? 0.5, right? If the step size is big, 0.5, you see that the Euler's method does very big error there, right? But the Runge-Kutta method is doing the pretty good job, right? It is close, but it is not perfectly fine, but it is close. Let me decrease the step size by factor 5, meaning what I'm doing is step size is 0.5, now I'm making it is 0.1, right? When I decrease the error, the step size by factor 5 in the Euler's method, what happens is the error will decrease by factor 5, but in the Runge-Kutta method, the error will be decreased by factor 5 to the fourth, right? That means 1/5 to the fourth, right? Almost 31/25. It will be less by the factor 31/25. So let me show you that. So you see that? So on the Euler's method, the error is a little smaller than the previous previous step size, 0.5, right? But there is still bigger. But when you do the RK4 method, Runge-Kutta method, what you see is there is almost no error. You see that? So this is how the error is decreased. Even the error is the step size is 0.1. So the Runge-Kutta method does very good job compared to the Euler's method. Okay.